Hello and welcome to the video focusing on midterm 2 review topics and some sample problems. Before we get started, let's talk about midterm 2 a little bit. The test will be 34 questions. It covers chapters 4 through 6, and you get the same amount of class time as last time, about 75 minutes for the test. It's multiple choice. Make sure to bring your Buck ID, pencils, erasers, etc. for the exam. We'll be sitting by a seating chart. You should have gotten that by email, I believe, yesterday. And I think that's just about all the information I have to share, other than maybe reiterating that the test is not cumulative, so it does not focus on any specific questions from chapters 1 through 3. Some of the topics, of course, come up again, like stoichiometry is a pretty big topic from chapter 3 that resurfaces in chapter 4, but we won't directly be testing the concepts from midterm 1. Looking ahead toward the final at the end of the semester, that test will be cumulative. And we'll talk more about that test in due time. Okay, so let's talk about some of the learning outcomes for Chapter 4. So we should be able to identify compounds as acids or bases and as strong, weak, or non-electrolytes. So acids we can recognize from our naming section. So we should be able to recognize, like HF, we can name it as an acid from Chapter 2, so we can recognize it as an acid here in Chapter 4. There are 7 strong acids. The strong acids are HCl, HBr, HI, HClO3, HClO4, HNO3, and then the very first H plus coming off of H2SO4, but not the second. So only the first H is strong. So these are our strong acids. Strong acids are strong electrolytes that happen to release H plus, and then the complementary or the conjugate ion into the solution. HF is weak. It only partially dissociates to H plus and to F minus. So this would be a weak acid. All of our other acids that we learned how to name would be weak acids and hence weak electrolytes. We have one prototypical example of a weak base, that being NH3, partially reacts in water to make some hydroxide ions. So making hydroxide ion is what it takes a substance to produce in water to call that substance a base. And if it makes just a small amount of hydroxide in solution, not a full stoichiometric quantity, we call the substance to be a weak base. So NH3 is a weak base. Technically, anything like it is also a weak base, like CH3, NH2, but we don't go through a lot of these examples. But you might recognize something that looks like NH3, maybe replace a hydrogen with some type of methyl group, would also be considered to be a weak base. Non-electrolytes are essentially all the other molecular compounds. So if you're thinking like ethanol, sugar, if you know a substance is not an acid of any kind, and it's not something that looks like ammonia, then that substance would be a non-electrolyte if we're considering molecular compounds. Now, when we look at ionic compounds are either water-soluble, and hence strong electrolytes, or they're just insoluble, and they're not any kind of electrolyte. An electrolyte is a property of a solution. An insoluble compound would not make a solution, so hence you couldn't classify it as any type of electrolyte. So we should be able to recognize reaction by type and be able to predict products from acid-base reactions. Also from precipitation reactions, those are by recognizing 2 water-soluble salts mixing to make an insoluble compound, using the solubility chart to predict that, and then using the activity series to predict when redox reactions should take place. So like a metal dissolving in a solution of metal ions or H plus ions, provided that that metal is more active or more reactive than the product metal or H2 that would form during the course of the reaction. We'll see some examples in our problems that we look at today. We should be able to calculate molarity and use it to convert between moles of substance and from volume and molarity. So molarity is just moles of solute divided by volume of solution. So we could take a particular quantity of a solution and know how many moles of solute we're delivering. We should be able to describe how to carry out a dilution to achieve a desired concentration or work through different types of dilution problems. We have an equation MIVI equals MFVF. For the initial molarity times the initial volume is related to the final molarity times the final volume. That works for dilution problems. It's not going to work so well for titration problems, so we can't use this equation for titration problems. We have to think about in titrations that reactions can be taking place. You can add an indicator to indicate the precise moment you have the right mixing of the stoichiometric amounts of your reactants. What we mean by that is, let's say you have some acid solution, let's call it H2SO4, and let's say you're adding slowly to that solution KOH. It's going to take 2 KOHs for every 1 H2SO4 to have the full reaction to K2SO4, AQ plus 2 waters to take place. So you have a certain quantity of H2SO4, there's so much of it present, say, in a reaction, and you're adding the KOH, say, dropwise, you're adding KOH through like a burette or something, so you're adding the KOH slowly, and you just have an indicator present such that when you add the right quantity of KOH, you get that color change to take place, so you can relate at that moment you've added twice as many moles of KOH as the number of moles of H2SO4 that were initially present. So we have to solve titration problems like reactions and use the ideas of stoichiometry within them. And if you're trying to cut corners, well, it may not work out so well for you. So just try to solve problems, being mindful of the correct way to solve them. Some key equations from Chapter 4. Molarity, moles of solute divided by volume of solution. It should be really well understood. If this equation is surprising to you, well, I would be surprised. Well, molarity is just related to the moles of solute times the volume of solution. So if you take a molarity, moles per liter, times the volume times the liters, you get moles. So your moles of your concentrated solution, so say your moles of your concentrated solution would be equal to that initial molarity times the initial concentration, or the initial molarity times the volume of that solution that we use. Then if you're adding pure water, then you get some diluted molarity, some diluted volume. So this would be the diluted volume would be your concentrated volume plus whatever water that was added. And the key is you're adding pure water. You're not adding to the moles of your solute. You're keeping that moles of your concentrated solution the same here. So this is still equal to the moles from your concentrated solution. So your MCVC is equal to MdIL-VdIL, or your M1V1 equals M2V2. And this works when you dilute. So this equation should make sense when we use it. We can use it for dilution problems and only dilution problems. If we try to apply it to titration problems, there's a good chance we may make a mistake or it may not work out with that particular problem. Let's look at some of the learning outcomes from Chapter 5. We should be able to describe the changes in potential energy that accompany the formation and breaking of chemical bonds. So if we have an ionic bond, so we have like a plus and a minus, in terms of like say Na plus and Cl minus, it's going to take energy to separate these ions. So if we want to separate these ions, we have to increase the energy and we have to actually physically pull those ions apart by the addition of energy. So there's something holding those ions together, so we have to have energy absorbed in order to break an ionic bond. If we have two like ions that are very near each other, so say two positively charged ions, then we're going to get energy released when we separate those ions. So the potential energy would drop if we separate two like charged ions. We could also think of the energy to break a bond, like say a hydrogen bond. That's going to have to absorb energy as well to release into two separated H atoms. So if we want to go back to having two H atoms, each with one electron, as opposed to having an H2 molecule sharing those electrons through the covalent bond, the hydrogen molecule would also have to absorb energy. We should be able to distinguish between the system and the surroundings in thermodynamics. The big thing here is like temperature changes are always of that of the surroundings. So whenever you see or think about the temperature change accompanying a reaction or a system, it's the temperature of the surroundings. So if you have like an exothermic reaction releasing heat, the surroundings temperature will go up. So the surroundings temperature increases as the system decreases in heat, or if the system's increasing in heat, then the surroundings are decreasing in their heat. So if a reaction is absorbing heat, then the surroundings is losing heat, the temperature is dropping. If the reaction is exothermic and releasing heat, then it's going into the solution, the temperature is increasing. That should make, hopefully, a lot of sense. So our Q reaction is just equal to the negative Q of the surroundings. This is our main idea in calorimetry, is that you're tracking the temperature of this and trying to relate that temperature change to the reaction. Very easy to do. because they're just related to each other by a simple minus sign and by a simple idea that all the heat from the reaction that's changed is being oppositely related to the surroundings. So we can calculate the internal energy from heat and work and then understand the sign conventions. The focus here is really on these sign conventions more than actually doing problems, because the problems don't make any sense, really. Like if you just get some random Q plus some random W and you can calculate delta E, well, that's great, but it doesn't really tell you a whole lot. What's really more important, I think, is trying to understand the sign conventions. We relate delta E generally for the system. So generally we're relating this for the system. The system is usually a reaction. So the system is the reaction that's occurring. So if you imagine a reaction that's losing energy, so you have a reaction take place, A to B, you're losing energy, then one of the things you can relate is that heat's being lost by the reaction, and then that can also be used into putting something into motion. So you can generally try to think of should the sign of Q and W be for a given change. And so W, we can relate to a couple of things. And so W can be related to the energy of motion. So it's like a force times a distance. Now, usually when you think of this, you're thinking of the surroundings. So if you want to put the surroundings, you want to apply a force to the surroundings so they can move some distance, then you're going to have energy lost by your system so that the system loses work, and then that work goes into the surroundings. So you would have the same W of the reaction is equal to the negative W of the system. So you might end up with these like negative signs in here, or just the idea being that if a reaction is putting the surroundings into motion, the reaction is losing work, has a sign of a negative value or less than 0. Then if the surroundings is kind of working on the reaction, doing work on the reaction, then the reaction's work is positive, it's gaining work, and the surroundings would be losing it. And so one of the simple analogies might be that if you have some sort of container, something inside the container, say a reaction is taking place, it's leading that container to decrease in volume, that's the surroundings doing the work on the system. The system's inside. So the system is being worked on by the surroundings. So in this example, the W sign for the reaction would be positive because it gained work from being moved by the surroundings. And then likewise, if you imagine the opposite scenario, if you have a container that's expanding by, say, some reaction taking place or something changing, so your system's expanding in volume, then that's the system pushing and moving the surroundings. So the system is working on the surroundings. The W sign here is negative. I like to think of it this way. If a reaction is heating up the surroundings, it's negative sign for Q. Q is negative in that case. And if likewise, if the reaction is working on the surroundings, moving the surroundings, that sign is also negative. So then if a reaction is absorbing heat, Q is positive for the reaction. And then if the surroundings are acting on the system, so if work is being absorbed by the system, like heat being absorbed by the system, the W sign is positive as well. So a big thing here with this point is trying to understand the sign conventions. And so then Q plus W would give you the sign of delta E. Delta H relates to Q, and Q specifically for an open system. I'm not going to go through the derivation, but I think the idea is for an open container at constant pressure, then the Q just simplifies to being related to delta H. So the concept of a state function would be like delta E and delta H are state functions, where for any type of system, delta E, like a reaction can release so much energy or can absorb so much energy, and then the magnitudes of Q and W can be anything it would take to make that happen depending on how the reaction's carried out. So the specific value of heat and work for a reaction, think about octane combusting in a car. Whether or not you're going 65 miles an hour down the highway or whether you're accelerating your car, the octane is being used in a slightly different way in those two scenarios, such that there's a different amount of heat being given off by those reactions and a different amount of work being given off by those reactions to put the car into motion. So the combustion reaction itself only has so much energy that it loses. So there's like a limit on how much heat or work can be done by that reaction, but that it could really be any magnitude of Q and W that add up to the proper delta E for the reaction. So Q and W would not be state functions, but delta E is. So then calculate delta H from delta E and P delta V. This isn't really anything I would concern ourselves with doing actual calculations here, other than kind of picking up that this is work. This is what the value of work is equal to. And then for the open system, the open container, then that's where that's going to end up canceling itself out and setting delta H equal to Q for the open system. So that's often said QP, or the heat of the reaction at constant pressure. Okay, and so then relating Q to delta H and indicate how the signs of Q and delta H relate to each other. That's exothermic and endothermic. So if delta H is positive, heat's being absorbed by the reaction. If delta H is negative, heat's being released by the reaction. For an endothermic reaction, again, it's going to cool down the surroundings because the heat that it absorbs comes from the surroundings. So the surroundings loses heat, and then vice versa. If the reaction releases heat, it goes into the surroundings. We have some more learning outcomes on the next slide for Chapter 5. So here are some more learning outcomes for Chapter 5. So use thermochemical equations to relate the amount of heat energy transferred in reactions at constant pressure, delta H, to the amount of substance involved in the reaction. So this just means if you have, some reaction, like ammonium nitrate is a common example, that this dissolves in water to form NH4+. In fact, we pass this around the room. I happen to remember that the delta H is about 25.7 kJs. So the idea of this point here is saying, well, what if you take like 3.00 grams of this? How much heat is released or absorbed by the reaction? So this heat here would be dependent for every 1 mole, because there's the 1 mole in front of NH4NO3. So this is the heat that's related for every 1 mole of NH4NO3, and then you can convert that to moles, multiply through, and see how much the heat changes for a certain quantity of reaction. And then positive means the heat reaction is absorbing energy, and negative means it would be releasing energy, if we had an exothermic reaction, as an example. So then calculate the heat transferred in a process from temperature measurements together with heat capacity specific heats. This is calorimetry. Some simple ideas of calorimetry that if you ask me, some people just try to cut corners and try to memorize the equations. It's such a simple derivation to say Q reaction, the heat change of the reaction is the opposite of the heat change of the surroundings. That's really, really basic. The surroundings of a coffee cup calorimeter, a constant pressure calorimeter instead of a coffee cup, is the solution that the reaction's occurring in. And then this simplifies down to a minus MCS delta T. And so your Q reaction, the heat released by the reaction occurring inside the calorimeter, is equal to the mass of the solution, specific heat of the solution, delta T of the solution. These types of problems will give you a CS, or say it's that of water, and that will be given within the problem. And you see that the CS is a joules per gram Kelvin. So you know you have to plug a mass in to the Q step to get the heat change of that reaction. Very easy problem to solve. And then the last thing you might do is relate the Q reaction, divide by the actual limiting reactant quantity in the reaction. So limiting reactant grams or moles, you could convert, or depending on the information provided, it might already be in moles. But if you get grams, then just do a molar mass conversion. Usually you're looking for kJs per mole, or for the delta H of some balanced reaction. So just remember, the Q reaction, that's the heat released by whatever the quantity of the reaction actually occurred inside of that calorimeter. And so you just have to go back through and set up a ratio for the joules or kJs per quantity of the reaction that actually occurred inside the calorimeter. So this works for your coffee cup. This works for your constant pressure calorimetry. Your bomb calorimetry has one minor deviation, and that Q reaction, still negative Q of the surroundings. And the surroundings are the entire calorimeter. And the calorimeter is described usually with one heat capacity term. So you might have one single C cal, like a heat capacity, including the water surrounding the calorimeter. If you notice a problem with bomb calorimetry, it should probably have the words bomb calorimetry right in it, so you recognize it. But then the heat capacity will just have a unit of energy per temperature, no mass unit. Mass still comes into play because the heat of the reaction is still dependent on the quantity of whatever the limiting reactant was in the reaction. So just search for the details, see that that's the heat release per quantity of reaction occurring, and then make whatever final conversions are needed to answer the actual question at hand. Hess's law is a big puzzle for piecing together multiple reactions, so we just have to manipulate the reactions, and then if we change the coefficients or flip a reaction, we just then, change the delta H accordingly. So if you have an A goes to B, delta H, say, is 10 kJs per mole, plus 10. If you flip the reaction to B to A, that would be minus 10. If you go 2B to A, delta H would be minus 20 kJs. And you're just trying to figure out how you can actually sum reactions up to get your desired reaction. Enthalpies of formation are kind of used to replace what you might ordinarily think of as absolute enthalpies. If you could measure the absolute enthalpy of all of your reactants and products in a reaction, you would very simply just take the absolute enthalpies of the products, take into account stoichiometry, and then subtract those of the reactants. Now, the only downside is that those values aren't easy to measure, but they're replaced with a value that kind of is synonymously used as if it were that same value, that being the enthalpies of formation. So the formation reaction kind of assumes forming 1 mole of a compound from its elements. If you do this for all substances in your reaction, all the substances are coming from the exact same set of reactants. So your reactants and products are related to the exact same set of reactants, assuming, of course, that your reaction is balanced properly. But then all you need to do is take the sum of your enthalpies of formation of the products, account for stoichiometry, and then subtract the sums of the enthalpies of formations of your reactants. So this is products minus reactants. And then we can use bond enthalpies, but this is the only part of this chapter that ends up being an approximation method, not an exact calculation. That's unlike every other topic in this chapter. So a little bit different with the bond enthalpies. We can approximate delta H by taking the sum of the bond energies of the reactants minus the bond energies of the products. So at first glance, it seems a bit strange because, one, it's an approximation, not a direct exact calculation. Then you're summing up the reactants minus the products. So that seems kind of strange at first, but it's just because you're saying how much energy does it take to break the bonds in the reactants, and then how much energy do you get back when you make the new bonds in the products. Breaking bonds always requires the absorption of energy. Like a molecule has to absorb energy to break its bonds. There's a reason why those bonds are being held in place, and there's a reason why that molecule is stable. So you have to have the molecule absorb energy to break those bonds. And if you have new bonds formed, then you're releasing energy as the new bonds are forming. So the formation of bonds is exothermic. The breaking of bonds is endothermic. Some key equations. Now, to me, there's a lot of equations in chapter 5, but most of these aren't direct equations that we ever actually use to solve problems. Like, for example, work is equal to force times distance. We're never going to give you a force and a distance and have you calculate work. This is an idea equation. This idea just says it's the energy associated with applying a force to an object to move it some distance. So it's the energy associated with, so work is the energy associated with putting objects into motion. The energy of electrostatic attraction is related to the charges of two particles divided by their distance of separation. So this equation is pretty easy. If you take a plus and a plus or a minus and a minus, and then separate them by some distance, then the energy goes up. So if you're bringing these particles together, you get a positive energy. That's not good in terms of the particles having some stability. But make it a plus and a minus, or a minus and a plus, and of course those particles then are attracted together and you get a negative energy. You get an energy of electrostatic attraction. So the closer you make two charged particles, the better. Of course, there will come a point where you don't want to keep pushing together because the electrons, like the remaining electrons in the atoms, will start to repel and the nuclei will start to repel. So like every molecule or ion has its like natural bond length. That, again, we're not calculating. We're not plugging numbers into this equation. This equation is just showing us that, generally speaking, the higher the magnitudes of these charges, the generally closer they are together, the better situated those ions are towards being attracted together. Delta E is E final minus E initial. This is just an idea equation. Again, we're not going to solve a problem with this, but a delta energy is just the energy of the final state minus the initial. Delta E is Q plus W. Again, we're not plugging Q and W in to solve for delta E necessarily, but we're just getting the idea that Q is the heat change of reaction, W is the work change. I like to think that W is only going to be negligibly large or non-negligibly large when you have a mechanical system. This is a chemistry class. So one of the ideas I like to talk about in my class is how W really has to be pretty small compared to Q for reactions occurring inside of chemical systems. And so we get H is equal to E plus PV. And so then if you do some rearranging for a delta H, this is how you get delta H to simplify to being equal to Q. I did a derivation in class. It's really not all that exciting. But for a reaction occurring at constant pressure, the heat change of the reaction is the magnitude of delta H. That's why we call delta H the heat of the reaction. Work is sometimes written as negative P times delta V. So if pressure is constant, the change in pressure, or there would be no change in pressure, the pressure would be constant. So for a change in volume, it would take work to be released by a reaction to expand the volume. And then if you contract the volume, then work is being done in the reaction. So this is just saying that if delta V is increasing, then the W for the reaction, think about a reaction that increases the volume of the container at constant pressure, then that reaction would have a negative W sign. And so then if delta V is a negative number, we're decreasing the volume of a container. This goes back to that container example we did earlier. If you decrease the volume of the container, then work is being absorbed by the reaction. The sign of work for the reaction would be positive. So this might help you understand some of the sign conventions for W. Again, we're not plugging numbers into this equation. We're just trying to understand the sign conventions for work with some of these equations. Some other equations, delta H is delta E plus P delta V, and then this simplifies down to being equal to QP. So this is just the definition of enthalpy. So again, we use this connection a fair bit so that we can track the heat change of a reaction related to delta H for systems occurring in open containers or for open systems. We even assume something like a bomb calorimeter is an open system. Not a big detail, but like when we start looking at bomb calorimetry problems, we're actually assuming that delta H is approximately equal to QP. I would say that this works for bomb problems and just any general type of chemical system. It makes a lot of the discussion of work somewhat strange because we do a lot of spend a lot of energy talking about work, and then when we get to a problem you might use it on, you kind of simplify it and make an approximation. But at least we're trying just to understand the sign magnitudes, or at least for your test coming up. If you understand the sign magnitudes of W, you should be well suited. If you're thinking about plugging numbers into some of these like obscure equations, we're not going to be doing that. So Q is equal to MCS delta T is the way I usually write this. Very easy to use equation. So the heat of a substance, if you're going to increase the temperature, heat has to be absorbed by the substance. So if temperature is going up, then heat's being absorbed by a substance. Then we can relate Q reaction to minus C cal times delta T. If you're memorizing this equation, then I don't know what to tell you. I mean, this equation here doesn't necessarily need to be memorized for a bomb calorimeter, but just understood as coming from the heat of the reactions opposite the surroundings. That's where the minus sign comes from. And then the calorimeter gets one constant because all the parts of the calorimeter are easy to reuse. So you have one object and its heat capacity used within those sorts of problems. Delta H of the reaction, products minus reactants, very easy to use equation. And then the sums of the bond enthalpies of the broken bonds and the reactants minus the formed bonds and the products for delta H. One little thing here, this being an approximation-based method, this is that final section that we cover, section 5.8. We didn't discuss anything out of section 5.9. I wouldn't worry about that particular section. It's kind of an interesting section because it talks about like energy and fuels and dietary type foods that we eat. So it's an interesting section, but nothing directly will come from that section on the exam. Okay, some learning outcomes for chapter 6. So we should be able to calculate the wavelength electromagnetic radiation, so calculate frequency and wavelength. So of course C is equal to lambda times nu. So the wavelength has units of meters. The frequency is the wavelength cycles that are completing per second. So this has a unit of inverse seconds. That's equal to a hertz unit. So meters times inverse seconds give you the units of meters per second for your speed of light. We should know the order of the different the orders of the different kinds of electromagnetic radiation. So like your gamma rays, your X-rays, UV. UV is greater in energy than the visible region. The visible region is greater in energy than IR, then microwave, then radio frequency. You won't have to know the specific wavelength regions here, other than I would know, and you probably already know this, that 450 to 750 nanometers is the visible region. And that going less than this is the UV, going greater than this is the IR. So just knowing where the light falls, and of course the 400 range is the blue light, 750 is reddish light. You get like a Roy G. Biv color, making your rainbow from 750 to 400. I wouldn't worry about what wavelength is associated to what color, but just that you're going to get the colors of the rainbow from 750 down to 400. So explain what photons are and be able to calculate their energies. So photons are just an individual light wave. We can describe the energy of a photon, E is equal to h nu, or hc over lambda. Should be able to use those equations very easily to calculate the energy. This is just the energy of one photon. Sometimes we ask for the energy per mole of photons. You might have to take this energy and multiply it by Avogadro's number, maybe convert joules to kilojoules. Planck's constant 6.626 times 10 to the minus 34, speed of light 2.998 times 10 to the 8 meters per second. Those are givens, but hopefully you've understood and mostly memorized those by this point. Explain how certain line spectra relate to the idea of quantized energy. So the whole idea of the Bohr model of hydrogen is so that we can understand the different energy levels of hydrogen. The idea that they're quantized gives us the idea that there's different orbitals that each have a different amount of space associated with that particular orbital, and there are various steps to other orbitals, so you can't just have any energy at all for one orbital to the next, that they take very distinct quantized energy levels, and you can calculate them very easily using the Bohr model for hydrogen. And then for larger atoms, we have to move towards a more simplified system, that just being electron configurations and quantum numbers and orbitals. And so the main equation to know, I think we just have to kind of memorize this one, is that the energy as a function of n for the H atom would be equal to minus 2.18 times 10 to the minus 18 joules times 1 over the nf squared minus 1 over the ni squared. Okay, so we just have to know that equation. And we could talk a fair bit about this equation on how, it kind of was derived off of or this is the equation for delta E for the hydrogen. But so the delta E for an H atom, calculated using this equation, it came from like the Balmer-Rydberg equation, which was 1 over the wavelength was equal to the Rydberg constant for hydrogen, then times 1 over an n1 squared minus 1 over n2 squared. And this was an empirical relationship that they found. Rydberg Bohr then related this equation and said, well, I can think about the energy of each H atom as being hc times the Rydberg constant. So this quantity here is actually the product of 3 different constants. This is minus hc times the Rydberg constant of hydrogen, at the energy of hydrogen of one single atom is just equal to minus hc Rydberg constant times 1 over the n value squared. I don't even know the Rydberg constant of hydrogen, but I do know this number. So this is like the only equation I ever use to solve problems, because what I like to think is, what energy change does an H atom undergo through a transition? How can we relate that to light? So like if we're thinking of our H atom, 1 to 2, I need to move this over. So let's over just a little bit. So from 1 to 2 to 3 to 4 to 5 to 6, these energy levels are getting closer and closer together. N equals infinity. When n equals infinity, then we have H plus an electron, an ionized atom at that point. So at some point we ionize. So you can imagine an atom in the ground state. This is the lowest energy level. That's why it's the most negative. Our hidden axis here is energy. So energy is going up on this axis. So we have one electron here that can be transitioning up to any of these energy levels, from 1 to 2 to 3 to 4. If the atom is going upward, then energy has to be absorbed. Light has to be absorbed, electrical energy has to be absorbed. And then if the electron is going from some high energy level back downward, then energy is emitted by that atom. So if we're going like 3 to 1, energy is emitted. If we're going 1 to 3, energy is being absorbed. We can get that very easily by calculating delta E for the H atom. So if you go from like 4 to 2 for hydrogen, so if you say, okay, if we have an electron here, we're going to take it down to 2. So the delta E final is 2. minus the initial of 4, the atom is losing energy, so delta H for the delta E for hydrogen should be negative because it's losing energy. Well, that energy is going into the photon. So the Bohr model allows you to very discretely think about the energy changes for H and how when energy is released by an atom, it could be converted into a photon, and then likewise, a photon can be absorbed to allow an atom to increase its energy level. And so then we can calculate the wavelength of moving objects, moving on into chapter 6. So objects in motion can have a natural wavelength. That comes from the Broglie wavelength. That's h over mv. We can relate the uncertainty principle that the delta x times m delta v must be greater than or equal to h over 4 pi, a fundamental limitation of quantum mechanics to know the simultaneous velocity and position of a particle. The electron is one that's really important. So our small, fast-moving particle then has the greatest issues in terms of behaving like a wave, and then a wave where we don't know exactly where it is at any given moment. So we start to think of probability distributions to understand electrons. So moving forward, we have to then relate quantum numbers to the types of orbitals that we see. So we see things like s, p, d, and f orbitals. Those are described by the L values of 0, 1, 2, and 3. And then the range of those values comes off of n. So the n value for an electron can be integral values from 1 on upward. The value of L has to be then 0, 1 on upward to n minus 1. So you can have a 1s, a 2p or a 2s, a 3d, 3p, 3s. So you can have all these different orbitals. The first time you get the f orbitals and the n equals 4 shell for like a 4f. Okay, now the idea of the electron configurations comes to the periodic table that elements are distributing their electrons into the most stable or lowest energy orbitals first. So you can look at nature to see what are the orderings of the elements in terms of the subshells. So you could look for subshells that go with 1 orbital for 2 elements across, to 6 elements across, to 10 elements across for like a D subshell, or 14 elements across for the F block. And you can kind of see where these are on the periodic table, just looking for the 2 and the 6 and the 10 and the 14 element regions. And then you can just kind of follow accordingly that your orbital energies just go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. Running out of space. Let me just do a couple more. 5p then would be 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. And if you're like not following where these numbers come from, just look at a periodic table and see that they're just coming right from the periodic table. So you should be able to get these right off a periodic table. High school chemistry often teaches something weird called the off-ball principle. The periodic table gives you the same information as that. And we don't even talk about that particular principle in this textbook and in our class. So we should understand radial probability distributions. There's a couple questions that'll come up with that topic in it, so I'll save a discussion for those. Explain how and why the energies of orbitals are different in many electron atoms from those of the H atom. So we can't use the Bohr model to understand larger atoms because the Bohr model doesn't work for systems that have more than one electron. So we have to use orbitals and electron configurations to understand larger atoms. We can draw energy diagrams to understand things like unpaired electrons and the Pauli exclusion principle and Hund's rule. So Pauli exclusion says each electron has to have a unique set of 4 quantum numbers in an atom. And then Hund's rule says we're going to maximize the spin of electrons in subshells when possible. So for like nitrogen configuration 1s2, 2s2, 2p3, we're thinking of our energy levels here. Energies going upward, so 2 electrons into a 1s, 2 into the 2s, and then we get 3 spin paired. This is Hund's rule being applied to H. So use all 3 p orbitals, spread those electrons out, maximize their spin. Then the periodic table we can use to write configurations. Down here there are some anomalies, but we're mostly concerning ourselves with understanding the configurations that we would expect, and we're not trying to have you memorize the anomalies. We can understand that some anomalies occur, or the idea is that an anomaly occurs is whenever the new configuration you get through the anomaly allows the atom to gain some extra stability. Some of the subshells are similar in energy, like the 4s and 3d, like the 5s and the 4d, like the 6s and the 5d, and then also the 4f, 5d, 5f, and the 6d. So there's just some passing of electrons to and from these different subshells. So we can understand where they occur. We can also make sense where they don't arise. We don't have any anomalies in the p block or in the s block, so just a few in the d block and in the f block. And sometimes they occur with the half or filled subshells, the resulting half or completely filled subshells being the driver of that gain stability. But not in every case. There are some, like in the 4F and the 5F series, there's a lot of weird anomalies there that are kind of hard to make sense of, so we don't generally try to make sense of them. We just try to understand that they occur, and that's about all we have in terms of learning outcomes for chapters 4 through 6. Let's look at a couple of equations for this chapter. So our equations for this chapter: C is lambda nu, E is equal to h nu, or hc over lambda. The Bohr model gives us that the delta E, or the energy for hydrogen minus hc Ribber constant 1 over n squared, and that equals minus 2.18 times 10 to the minus 18 joules. I would just memorize this number here. I would also then probably just memorize that delta E is equal to minus 2.18 times 10 to the minus 18 joules, and then 1 over the nf squared minus 1 over the ni squared. So I think the energy is a function of n for hydrogen is this equation. Either memorize that or memorize this equation, or just the two together. I wouldn't bother memorizing the Balmer equation, the 1 over the lambda value, because it just is a little too much to memorize. I think one equation relates to energy change for H. Relate that back to the photon of light through a second step if you need to. Then the Broglie wavelength uncertainty principle, I think we just have to understand and be able to use those equations if given problems on those topics. Okay, so let's go over some sample problems. These are mostly taken, or at least roughly the first 3/4 of the problems I'll talk about today come from the spring 18 midterm that was given last spring in 1210. So the first question: given the reaction below and the average bond enthalpies, calculate the enthalpy for the reaction. So we're given the bond enthalpy of the nitrogen-nitrogen triple bond, the O2 double bond, and the NO double bond. Okay, so what I need to do is take the NN bond, break the O2 bond, we're forming 2 of the NO bonds. These are the kJs per mole of the bond. So 1 mole of N2, so 941 kJs, plus 495 kJs per mole for O2 times the 1 mole of O2 bond that needs to break, then minus the reactants, 607 kJs per mole, and there's 2 moles of that bond. There's 2 bonds forming. So I need to double the 607. So 941 plus 495 minus 2 times 607. Okay. I'm not going to go through the math on some of these answers. You can check it on your own. But the key here is the broken bonds and the reactants minus the formed bonds and the products. Photons hit the surface of a metal with a wavelength of 435.0 nanometers. If no electrons are observed to be ejected from the metal, what modifications to the light source could lead the electrons to being ejected? So we're having light hit a metal, and then you have some detector set up so that if electrons were to be emitted, they would be observed. Now the idea is that the photons have to carry enough energy per photon to be greater than the ionization energy of the metal. So if we increase the intensity of the light source, that just means throw more photons. That's not going to work. If we decrease the wavelength, think about the energy of a photon, hc over lambda versus h nu. If we want a greater energy photon, we need to increase the frequency or decrease the wavelength of the light source. So decreasing the wavelength could work. So only 2 would be the right answer to this one. So the intensity doesn't work. We need to up the energy of the photon by decreasing the wavelength. Helium gas is compressed as shown. What is the sign of work for the helium gas during the compression? So we have helium inside, that's our system. So our system, if it's going to decrease in volume, has to be worked on by the surroundings. So the surroundings has to do work to push inward on that piston. So the surroundings are doing the work, the system is absorbing the work. So the sign of the system absorbing work, W, would be positive. So work's being absorbed by the reaction because it's worked on by the surroundings. If work is done by helium on the surroundings, this would be a negative sign for W. So the negative, if work's negative for a reaction, then that would be the explanation that helium is working on the surroundings. That would have to lead to an expansion of the helium, not a contraction. So if the container expands, work sign would be negative because helium would then be working on the surroundings. Is the following reaction an oxidation-reduction reaction? If so, which atom is reduced in the reaction? So this just has to do with the oxidation numbers. Oxygen, unless it's one of our exceptions. Exceptions are peroxides, superoxides, and then compounds with fluorine. This isn't one of them, so this just has to be an ordinary -2 oxidation number oxygen. So a +2 for carbon. Hydrogen's a +1. Hydrogen's +1 in molecular compounds, -1 in ionic compounds. CaH2 is a good example of an ionic compound containing hydrogen. Calcium, of course, is a +2, making hydrogen a -1. So hydrogen's +1 here, oxygen's -2. Oxygen's still -2 in CO2, -4 overall. Carbon's a +4, hydrogen's a 0. Reduction is gaining. Gaining electrons is reduction. Losing electrons is oxidation. Leo the lion goes grr, or oil rig are two things most people use. So we want to know which atom has gained electrons. So oxygen is the same, so oxygen is unchanged. Hydrogen goes from a +1 oxidation number to a 0. So that's hydrogen going from 0 electrons, each of them is gaining an electron. So we have hydrogen gaining electrons. So H is gaining electrons, so it's reduced. So it is an oxidation-reduction reaction. Carbon is losing electrons. So each carbon is losing 2 electrons. Losing electrons is oxidation, so the carbon is oxidized in this reaction. So each carbon's losing 2 electrons, and each hydrogen's gaining 1 electron, and we just have twice as many hydrogens as carbons to balance it all out. According to the Heisenberg uncertainty principle, it is impossible to simultaneously know both the position and you can either answer velocity or the momentum. So the momentum term will be delta mv. Mass of most particles is constant, so a lot of times you can rewrite this as m delta v. So the uncertainty of the velocity or the momentum cannot be simultaneously known as a position. So spin, charge, and mass are just kind of incorrect choices. So 400.0 grams of water at 22 degrees is added to a coffee cup calorimeter. Then 25 grams of HCl gas is dissolved. I don't know who wrote this test. They can't do simple grammar, I guess. But so you mix water and HCl gas, the temperature of the resulting solution increases by quite a bit. What is the enthalpy of solution in kJs per mole? I was going to say, well, it's exothermic. Well, all of the choices are exothermic, so unfortunately that's not going to help us. We're going to have to solve and get this problem right. Q reaction, negative Q of the surroundings. The surroundings is the solution, so negative Q of the solution. The solution is mostly water described by a pure substance, MCS delta T, except we can plug in the mass of the solution, 425 grams. Specific heat, 4.184 joules per gram Kelvin. And then the final minus the initial temperature, so that's 50.8 minus 22.0 degrees C. And so I will actually work this one out because I want to do the next step. So minus 425 times 4.184, and then times the temperature change, 50.8 minus 22, gives us, and I'm going to convert that into joules, kilojoules by dividing by 1,000. So 1,000 joules per kilojoule give this to be minus 51.2 kJs. Now, you may look and say, aha, that's the right answer, but not so fast. What we have to do is say that this is the heat that's released per quantity of the reaction occurring. That's per 25.0 grams of HCl. So we could convert and say, well, that's the kJs per gram of HCl, but per mole, we want per mole of HCl. So we want the enthalpy of solution per mole of HCl, so we just go grams per mole. 35.45 plus 1.008, so that's 36.46 grams per mole. So I'm going to divide by 25. So divide 51.2 by 25 and then times 36.46 gives 74.7 kJ. So minus 74.7 kJs. So choice A. Okay, what is a possible magnetic quantum number for an electron in a 3p orbital? Okay, so N is the principal, L is the angular momentum, M sub L is the magnetic, M sub S is the magnetic spin. So size, shape, orientation or direction of the orbital. The number of M sub L's gives you the number of different possible orbitals in the subshell. N defines a shell, N and L together define a subshell. And M sub L define an orbital, and then an electron is given by all four of these, and each electron in an atom has to have a unique set of 4 quantum numbers, has to have its own space to occupy. Okay, so the magnetic quantum number, we're going to know the M sub L that's possible for a 3p orbital. So the p orbital has an L of 1. The p is given by L1, S is L0, D is L2, F is L3. So the range of M sub L's, if L is 1, is minus 1, 0, and plus 1. So a possible M sub L value, a possible magnetic quantum number, could be 0, but it can't be minus 2, can't be 3, can't be a half. D would be a possible quantum number if we're talking about the magnetic spin quantum number. And then it can't be 3 or minus 2. You'd have to have an F block or a D block to give rise to the possible M sub L's of 3 or minus 2. Which compound below acts as a weak electrolyte and a weak base in aqueous solution? So this is a weak acid, HNO2 is, so it's a weak electrolyte. NH3 is our prototypical weak base, weak electrolyte. NH3 reacts in water to partially produce some hydroxide ions and some ammonium cations. But it also remains as a fair bit of unreacted ammonia and water molecules. So we only get a small amount of our product, just a relatively small amount. Like HNO2 produces a small amount of H plus ions in solution and NO2 minus, not a full. So we get a partial formation indicated by the equilibrium arrows. Magnesium hydroxide is just insoluble, so we don't get any hydroxide ions for that one. And then methanol doesn't release any hydroxide ions. It's neither an acid or a base. It's a non-electrolyte. So non-electrolytes aren't producing hydroxide ions in solution. So the best answer here for the weak electrolyte, weak base would be the basic ammonia molecule. So 10, the standard enthalpy of formation of anthracene, the standard enthalpy of combustion of anthracene, C14H10, is minus 7059 kJ per mole. What is the enthalpy of formation of the compound? And we're given the enthalpy of formations of CO2 and water. And so the idea here is that the delta H of this reaction comes from the combustion of 2 moles of C14H10. This is the combustion reaction of the compound, all balanced out for us. So the delta H of this reaction would be the combustion enthalpy of the compound times 2 moles. So it would be minus 7059 kJs per mole of the anthracene times 2 moles of anthracene, because there's 2 in front of that compound in the reaction. So the delta H of this reaction is like 14,000 something, so 7059 times 2, so minus 14,118 kJs. Now that delta H is the one that corresponds to the products minus the reactants in terms of delta HF values. So we can take 28 moles times the delta HF of CO2 plus 10 times the delta HF of water in the liquid state, and then minus 2 moles, so it's 10 moles times the delta HF of water. So then 2 moles times the delta HF of anthracene, and then the delta HF of oxygen, of course, is 0 because that's the element in its standard state of oxygen. So we have to remember that to plug into the problem. So we're taking the sum of the products minus the sum of the reactants, standard enthalpies of formation, and setting those equal to the delta H of the reaction. So we could have given you the delta HF of this, this, and this, and we could solve accordingly for the delta H of the reaction, but this problem is actually giving us the delta H of the reaction and having us solve for this quantity here. So we just want to plug in, and I'll work this out. So I'll do 28 times minus 393.5 plus 10 times negative 285.83, hit equals. So that's minus 13,000 and some change. So this works out to be minus 13,876.3 kJs minus 2 moles times delta HF of anthracene equals minus 14,118 kJs. Okay, so where do we go from here? Let me make this a little smaller. Move this out of the way. Whoops. Okay, so where do we go from here? Well, I need to add this quantity to both sides. So I need to do that answer, negative of it, plus minus 14,118. So I get, by adding 13,876.3 to both sides, I get minus 241.7 kJs equal to the minus 2 moles times the delta HF of anthracene. So I need to divide both sides by minus 2 moles. To get the delta HF of A. So that works out to be plus 121. Okay, so my sign goes away, plus 121 kJs per mole. So kJs per mole. Okay, so it's just products minus reactants, and it's just taking the delta H of the reaction and setting it equal to the products minus the reactants to solve for one of the unknown delta HFs in that problem. So to prepare 500.0 milliliters of 0.250 molar aqueous solution of glucose with a given molar mass, how much glucose should be used and what procedure is best to prepare this solution? Okay, so it says take 45 grams, fill to 500 liters, 45 grams into a volumetric flask, and then fill it to the 500 milliliter mark, and then add glucose. Okay, let me say this again. So it says that we're filling to the 500 mark with water, then adding our glucose. That's the wrong procedure. So like A is not going to work. B, let's see, 45 grams is how much it takes. Let's work out the mass real quick, okay, because that's part of the problem here. So we want half a liter of 0.250 molar solution. So how many grams of glucose does that take? Well, we want 0.250 moles of C6H12O6 per liter. We want there to be half a liter. And then 1 mole of glucose has a molar mass of 180.2 grams. So we can solve for the mass right off the bat, so we can narrow in onto one of these answers. 0.25 times 0.5 times 180.2 gives me 22.5. So I want C or D here. So 45 is too much. So 22.5. So take 22. So fill a volumetric flask to the 500 mark, then add the glucose. That's not the right procedure. We want to place the glucose in the flask, then fill with water as it dissolves, so that we get the solution volume to be a total of 500 milliliters. So this would be 500 mils of water, then plus the glucose. We want 500 mils of solution. So only step D is appropriate. So in general, what characteristic distinguishes a reaction with a delta H greater than 0 from a delta H less than 0? So a reaction leading to weaker bonds in the products and the reactants, a reaction leading to stronger bonds in the products and the reactants, a reaction leading to the formation of new bonds in the products, and a reaction which leads to, which must break bonds in the reactants. Okay, well, breaking bonds is endothermic, forming bonds is exothermic, but most reactions are characterized by the bonds of the products compared to the reactants. So we're breaking bonds and then making new bonds. So this is the sum of the energy to break our bonds in our reactants minus those that we form in the products. Okay, and so whether or not a reaction looks like this example here, this would be an exothermic reaction, or if it looks like one that looks like this reaction here, which is an endothermic reaction, has to do with whether those bonds in the products are stronger or weaker than those in the products. And so I think we actually had problems with this in the spring, if I remember. So a reaction leading to weaker bonds in the products than in the reactants is, so if we have weaker bonds in the products than the reaction, that would be endothermic. So this is what choice A is saying. And then choice B is saying a reaction leading to stronger bonds in the products than in the reactants. This is what B is saying. So it's a poorly worded question because I can see how A and B could be correct. So if what distinguishes an endothermic reaction from an exothermic? An endothermic reaction is choice A. I think A is probably the right answer to this question, just because it's saying that the endothermic reaction would be the one that's leading to weaker bonds in the products than in the reactants. So that's what's distinguishing the endothermic reaction from an exothermic reaction. Okay. So the idea is weaker bonds, endothermic in the products, stronger bonds in the products lead to the exothermic reaction. When 1 mole of each compound below is dissolved in 10 liters of water, which solution has the greatest chloride ion concentration? So all of these compounds are water-soluble ionic compounds. So if you take 1 mole of AlCl3, you're getting Al plus 3 Cl minus. When it dissolves in water, you're getting 3 moles of chloride ion. So this solution here would be 3 moles of chloride per 10 liters of water. Two leads only to 1 mole of chloride, and 3 leads to 2 moles of chloride ion. So we're getting most chloride ions from AlCl3, and hence the greatest chloride ion concentration. So when we dissolve a mole of each compound in the same quantity of water, we're going to get a greater chloride ion concentration from the compound that releases more chloride ions into the solution. The following diagram represents a compound dissolved in water. Which compound might be represented? Okay, so what we have are some intact molecules. We have some ions that have been separated. So what it looks like that we have here is the case of having a weak electrolyte, because we have some intact molecules, some ionization. So HCl in water would be a strong electrolyte. So all the molecules should have been broken apart if it's HCl. So B doesn't make any sense. C is a non-electrolyte, so that doesn't make any sense. KBr is a strong electrolyte. It should be completely dissociated in solution, so that doesn't make any sense. So the only one that makes sense here is the weak acid, weak electrolyte, HF. So we have some intact HF molecules, some of them have dissociated. So A makes the most sense. A photon in which region of the electromagnetic spectrum is characterized by a shorter wavelength than a photon in the visible region? Okay, so we have a visible region photon. You go to a shorter wavelength, E is equal to hc over lambda. So if you go to a shorter wavelength, that's going to go to a greater energy. So infrared is the lower energy region, ultraviolet's the higher energy region. So ultraviolet would be shorter in wavelength than a photon in the visible region. The electrostatic interaction of two oppositely charged ions is best described as an attractive potential energy, attractive kinetic energy, repulsive kinetic energy, repulsive potential. So it's attractive potential energy. So bond energies are potential energy. Kinetic energy is the energy of motion. So you put two things into motion, 1/2 mv squared, that's kinetic energy. Bond energies, electrostatic attraction, these are all potential energies. Photons of which wavelength possess an energy of 325 kJs per mole? Okay, so what we might do is work out the energy of one photon. So we can relate that to hc over lambda. So we need to know the energy of just one photon. So if it's 325 kJs per mole, we would take 1 mole, be Avogadro's number, the energy of just one photon, gets rid of photons, get rid of moles, and then do one final conversion, 1 kJ, 1,000 joules. Okay, so 325 divided by Avogadro's number and multiplying by 1,000 gives us an energy of 5.397 times 10 to the minus 19 joules. And so then from there we can plug that in to solve for the wavelength. Wavelength would be hc divided by E. So take this energy, plug in, divide into h times c, and that should give us the wavelength of light. It's probably A or D. The reason why I would guess A or D, this is a relatively high energy. I guess it could be B as well. So it's probably not C. C is an infrared photon. It's going to be much lower in energy than that particular value. So just plug it in and solve. Number 20, which solution when added to an aqueous solution of K2SO4 leads to the formation of a precipitate? Okay, so all ammonium salts are soluble. KOH, all potassium salts are soluble. So like NH4 to SO4, that's not insoluble. That's aqueous, as is KOH. So that's not going to lead to a precipitate. What about strontium sulfate? Well, here you could go check your solubility chart. If you forget, it's lead, mercury, 1 ion, strontium 2+, barium 2+. So this is going to be only 2. So strontium sulfate leads to the formation of precipitate when mixed with K2SO4. Student constructs the following diagram for a 2p subshell for an O atom. O should be a 2p4 configuration following the 2s2 and 1s2. So 1s2, 2s2, 2p4. Is this correct? Of course it's not, because these two electrons here have the same set of 4 quantum numbers. They violate the Pauli exclusion principle. We should have had 1 up, 1 down, then the 2 upward. So these two are following Hund's rule by using 2 orbitals, maximizing their spin, and then spin pairing then satisfies the Pauli exclusion principle. So this is the wrong answer, wrong reason. It's not about maximizing the spin of the electrons. We need to spin pair 2 electrons in the same orbital so they don't have the same quantum numbers. No, so is the diagram correct? So no, 2 of the electrons have an identical set of quantum numbers is the correct answer. No, it violates the uncertainty principle. It has nothing to do with this question. Yes, it maximizes the spin of the electrons. We can only maximize up to 3 electrons in a p subshell in the same direction. That 4th one, we got a spin pair. Given the following thermochemical equations, determine the enthalpy of the reaction in Kj. So we want this reaction here. Okay, so this is kind of a puzzle, but hopefully once you get good at these, they're pretty easy to construct. Like I just look for NF3 first. It's only in one reaction. It's actually perfectly written with the first one. We don't need to change anything because I get 2NF3, 2NF3. Let's look for copper. We see copper here and only there. So that's actually good. So I'm going to take this reaction here. I'm going to add that one up as well. And then the final thing I might look for is balancing everything else out to give our reaction. And so then it actually may look like we just take reactions 1 and 3 and add them up. But they don't quite balance out to the desired reaction. So we actually need to take this reaction here, double it, and flip it. So I'm going to go -2 here. Why am I doing that? Well, I don't want NO in my balance reaction. So the balance reaction doesn't have NO in it. The first reaction has 2 NOs in it. So I need to put 2 NOs on the product side. So I'm going to flip this reaction here, right? 2 NO here. And then F2 from doubling that. And then, the F2 is over here, plus the NO. So the F2 gas is over here. And then on the opposite side was the original product in the reaction since we flipped it. Now 2 NOF. Now this works, or the delta H of this reaction has to be double of what we started with in the negative. So I need to take the minus 156.9 kJs and multiply that by -2. So I'm going to take delta H1, delta H2, and my delta H3 is equal to this. So my new delta H is delta H1 plus delta H2, and then plus delta H3. So just minus 82.9 plus minus 531.0, and then plus -2 times minus 156.9. So assemble your puzzle, change your delta H's accordingly, take into account flipping with the minus sign, changing the coefficients with the proper value, and solve accordingly. What is the concentration of a solution of H3PO4 if 15.75 milliliters of 0.125 molar KOH is required to fully titrate the acid? 50 milliliters of the acid. Okay, now the actual problem in the example had the reaction written out, but we don't need the reaction to be written out. We should be able to write that as well. So we can take our acid, aqueous acid, we're adding KOH. Now the idea is we're going to remove all of those H's, all the acidic hydrogens. We know they're acidic because they're like part of the acid. All the H's that we know to be acidic are removed. Like we're going to go down to that base ion that we learned how to name. So we're going to go all the way down to PO4 3-. So K3PO4 plus H2O. So acid plus a base goes to a salt plus water. And so then we get 3 waters. We need 3 KOHs to put everything into balance. So what this reaction is telling us, for every mole of H3PO4 initially present, we need to add 3 moles of KOH. So if we initially have 50 milliliters of acid, we want to know the concentration of that solution. So H3PO4's concentration will be the moles of H3PO4 in that solution divided by the volume of that solution. Volume of the solution in liters is 50 milliliters, so 0.050 liters. This is what we need to solve for using our stoichiometry. So the moles of H3PO4, we use the volume of the KOH and the concentration of KOH. So if we take 0.01575 liters of KOH times 0.125 moles of KOH per liter, the volume cancels. We get the moles of KOH. 3 moles of KOH had to be added for every 1 mole of H3PO4 originally present. So that gives us the moles of H3PO4. So we take the moles of H3PO4, divide by, again, the volume of that solution. It's 0.01575 times 0.125, divide by 3, divide by 0.05. So we get 0.0131. So C. Okay, so we can write reactions for acid-base reactions. Acid plus base go to the full ion, all the H's removed. H3PO4 is a weak acid. KOH is a strong base. They go to full completion. The weak acid just doesn't completely dissociate in water, but it'll completely dissociate in the presence of strong base. Completely dissociate all the way to PO4 3-. So hopefully you find that writing these reactions is pretty easy, and then it's just a stoichiometry problem. And all you got to do is solve it accordingly and understand the steps, and hopefully these problems are pretty easy. So what is the range of possible angular momentum quantum numbers of L, so that's L, when n is equal to 4? So when n is 4, the range of L's would be 0, 1, 2, and 3. So L can be 0, 1, 2, or 3. So it could be any of those. So meaning we could have 4s, 4p, 4d, or 4f subshell. The enthalpy of which reactions below is or are equal to 0? So we're given a couple things. The enthalpy of combustion of H2, the enthalpy of formation of H2, the enthalpy of combustion of CH4, the enthalpy of formation of CH4. Okay, the enthalpy of combustion of CH4 is this reaction here. So CH4 plus O2 goes to CO2 plus 2 waters. This is the enthalpy of combustion reaction of CH4. The delta HF reaction of CH4 would be CH4 as a product, 1 mole of it, and then carbon in its most stable state, carbon solid graphite, plus 2H2 gas. Likewise, the combustion reaction of H2 would be H2 and O2 combining to form water. So 2 of these, 2 of those. The delta HF reaction of H2 would be H2 as a product coming from its constituent element in its standard state, which is also H2. So the delta H of this reaction, of course, is defined to be 0. So the enthalpy of the formation reaction of H2 is the only reaction that should be 0. Now, why are the others not 0? H2 and O2, this takes place with the flame. We know that delta H is not 0. Energy is being released here. Delta H is definitely less than 0. Same thing for the combustion of methane. We know energy is being released here. We know that's an exothermic reaction. Now, the formation reaction, I may not know if this is positive or negative, but for forming compounds, they have some enthalpy associated with forming a compound. It's only the elements that have 0 enthalpies of formation by definition. So we're only looking at 2 here as being the only answer. So the net ionic equation for the reaction between solutions of hydrofluoric acid and KOH. So HF and KOH. Looks like a naming problem, but you can see from the choices we can certainly work those out. Okay, so HF's weak, KOH is strong. So full ionic reaction would be HF, or let's even think of the full molecular reaction first. So the full molecular reaction would be KF plus water. Acid plus base goes to the salt plus water. So that's easy enough. And then the full ionic would be writing K plus OH minus goes to K plus F minus plus H2O. So I can only separate strong electrolytes. I can't separate weak electrolytes in solution. So I leave HF intact, separate KOH, cancel out the spectator ion K plus. So the net ionic equation should be just HF plus OH minus goes to F minus plus water. Okay, K is still there, it doesn't really disappear, but it's just canceled out for the net change taking place in the reaction. So HF plus OH minus goes to H2O and F minus. Which atom possesses a total of 3 unpaired electrons? Okay, so that's neon configuration, 3s2, 3p3, so that 2 electrons in the 3s been paired, and 3p, 3 electrons been paired. So definitely phosphorus. Now what about cobalt? Cobalt has an argon 4s2 3d7 configuration. It's the 7th transition metal over, right next to iron. So 4s, 2 electrons, and then D block gets 1, 2, 3, 4, 5, 6, 7. So we have a net 3 unpaired electrons for cobalt as well. Okay, so both of them have a total of 3 unpaired electrons. All right, so let's take a look at this one. So we have iron and aluminum. Specific heat's given. Aluminum has the greater specific heat. If you have equal quantities of each metal at minus 25 degrees, and then they're added to water at 250.0 grams at 25 degrees C, which metal is going to cause the greatest change in the temperature of water? So will iron increase the temperature the most, or decrease it by the most, or will aluminum increase the temperature by the most, or decrease it by the most? Well, both of the metals are cold, colder than the water. So their temperature, their heat's going to increase, and water's heat is going, and its temperature therefore will decrease until they're equal to each other. Okay, so we have a Q of the metal versus the Q of the water, and they're inversely related. So we know the metal's temperature is going up and the water's temperature is dropping in the particular example here. And so then you could think of the MCS delta T for the metal as it relates to waters. Okay, so the final temperature of water is going to be dropping to match the colder temperature of the metal as it starts to rise until they equal each other at the exact same temperature. Now we could plug numbers in and see, like that's one option that we would have within this particular problem. Another way you can think through this analogy, though, without necessarily plugging numbers in, would be to maybe relate this to the problem we've solved before, which is like if you have hot iron and hot aluminum, which one would cause a greater change in water? So if these were hot, so say these metals were at 100 degrees C, you're adding them to water. So the water temperature would be increasing in that example. And so then the metal with the greater specific heat would have absorbed more heat and therefore would have more heat to give water to increase its temperature by the most. So if we're talking about which metal would increase the temperature of water by the most if they were hot metals, then it would be aluminum, the one with the greater specific heat. So now if we're considering the metals being cold instead of hot, so we have cold iron, cold aluminum, both at the exact same temperature, then aluminum would have lost more heat upon cooling, so it's going to be able to pull more heat out of the water, so it's going to cool water down by the most. Now, if you're confused at why aluminum is the right answer, you could always plug numbers in. You could always just go ahead and solve for the TF. It's a lot of algebra, so it's pretty tricky, but you can just set up your Q of the metal minus Q of the water, MCS delta T for the metal, minus MCS delta T for water, and try plugging in, 0.45 versus 0.9. You'll see that aluminum is going to pull more heat out of the water, dropping the temperature by the most if you do that math, which I don't think you have to do, but if you need to, that's a possibility. So using the Blow reaction and the standard enthalpy reaction, how much heat is released or absorbed when half a mole of ethane completely combusts? So energy is being given off because it's exothermic, negative sign. So heat is being released in the surroundings. Endothermic reactions would absorb heat from the surroundings, so it's not B or D. And then this is the heat change for every 2 moles of C2H6. Why 2 moles? Because there's a 2 in front of C2H6 in the reaction. And so then the heat of the reaction for half a mole of ethane would be 0.891 divided by 2, then multiply by 0.5. So it's going to be the smaller of the two numbers. So 223 kilojoules is released to the surroundings. Which of these transitions of an electron of the H atom requires the most energy to be absorbed? So H absorbs energy when electrons go from a low N to a high N. And then the energy levels are getting smaller and smaller together as we go up. Okay, so the most energy to be absorbed, we got 2 to 3. So that's energy absorbed, 2 to 3. 2 to 1, that's releasing energy, so it's not going to be 2 to 1. 3 to 4, that's absorption of energy. There'd be a lower amount of energy than 2 to 3, though, so it's not going to be that one. And then 5 to 4, that releases energy, just a relatively small amount of energy, so that's not going to be the answer either. So just A. So the most energy to be absorbed by hydrogen, low N to high N. And the low N to high N, 2 to 3 is a greater energy than 3 to 4. 1 to 2 would have been even greater, but that's not one of the choices. Zinc is observed to dissolve in an aqueous solution of cadmium, but not in a solution of rubidium. Rank the metals in the order of increasing activity. Okay, so since zinc does not dissolve in rubidium nitrate, that means that rubidium solid is not formed in that reaction because rubidium solid must be more reactive. So the most reactive metal here would be rubidium. The zinc is dissolving in cadmium. So cadmium solid is forming, so zinc solid reacting with CdNO32 to form zinc nitrate plus cadmium solid. Since we're getting this solid here, must mean that this cadmium solid is lesser reactive than zinc solid. Zinc solid is reacting because it's more reactive. So we're going to go rubidium, zinc, and then cadmium. Rubidium is the least reactive, then zinc, then cadmium. 36 shows us a probability function for which orbital. Okay, so a 1s orbital has one peak, no nodes. A 2s has a node and one peak. So the number of peaks is actually telling us the n value here. So this is going to be a 3s orbital. Okay, so a 3s orbital should have 2 nodes. So 2 radial nodes for a 3s orbital. Now, we didn't quite talk about 2p functions exactly. So the only minor confusing thing is why 2p is a choice here. What does a 2p orbital look like? Well, a 2p orbital just looks something like this. So there's no radial node on a 2p orbital. And it's, maybe not the greatest guess here, but no radial nodes on a 2p orbital. Certainly not 2. Okay, so it's not the 2p orbital, not a 2s or a 1s. So 3s is the best answer. So we're really only counting radial nodes. They're only shown in our textbook for s orbitals. So we're mostly just taking s orbitals as our basis for determining radial nodes. The angular nodes are determined by the angular momentum quantum number. So all the s orbitals have an L of 0, hence 0 angular nodes, 2 radial nodes. So an angular node would be like the p orbital node at the axis of the atom. So that would be an L of 1 for one angular node. The radial nodes are on the radius of the atom. So that's why they take a slight different term in terms of the node. So radial node versus an angular node. So like the total nodes for 3s would be still 2. Which quantum number must be different for the 2 orbitals shown below? Well, those are d orbitals. So one is, these are hard to see the way they're printed. So this is in the xz plane. So that's the dxz orbital. I don't know if you need to know that per se, but it's just where the symbols come from, is it's in the xz plane. And it's because it's intersecting the axes. And then the other one looks like it's in the YZ plane. So that's the DYZ. That's really not part of the problem per se, but we just have 2 different d orbitals shown here. And so what must be different for these orbitals is they must have a different magnetic quantum number. So these are just relating to orbitals that have the same n, the same L, hence they're in the same subshell. So they must differ in their magnetic quantum numbers. Each orbital can contain 2 electrons, so an electron in those orbitals could have a plus or minus half spin, so they don't necessarily differ in the magnetic spin quantum number. Phosphoric acid can be prepared by the formation of P4O10 with water, as shown by the reaction. So we got 25.8 grams of phosphoric acid is produced. When 25.8 grams of phosphoric acid is produced, 10.9 kilojoules of heat is evolved. That's another word for released. So the delta H of the reaction, the Q reaction would be minus 10.9 kJs. It's releasing that much heat. And then per 25.8 grams of H3PO4, and we need to use the molar mass. It's given 98.0 grams per mole of H3PO4. And then the reaction has 4 moles of H3PO4. So we need to quadruple that heat. So we go from grams to moles. Moles cancel, so we get just kJs. So it should be negative, not positive. Exothermic reaction. And probably looking at A once you do the arithmetic. I'm actually just guessing that it's A, but okay, so let's move on to the next. Identify the oxidizing agent and the reducing agent in the following equation. Okay, so copper goes from 0 to a 2+. So copper is losing electrons, copper is oxidized. H is what's being reduced. So H is reduced. Oh, sorry. H is unchanged. It's actually nitrogen that's undergoing the change. So nitrogen is originally a +5 and it's ending up in a +4. So nitrogen is the atom that's being reduced. So N is reduced in this particular reaction. H is unchanged, O is unchanged. And so the oxidizing agent is a substance that facilitates the other substance being oxidized. Okay, so the oxidizing agent is actually the thing that's reduced. So the agent of oxidation is nitric acid. It's a substance that contains the N atom. And then the reducing agent is the thing oxidized because it facilitates something else to be reduced. So the reducing agent is the copper. So copper solid is the reducing agent. And then the HNO3 is the oxidizing agent. The agent means it's not the thing that undergoes that step. The oxidizing agent is not oxidized. It allows something else to be oxidized because it's reduced. Now, the only reason why these terms pop up is usually you define atoms as either being oxidized or reduced, and then the substance containing those atoms as being the agent. So nitric acid is what you define to be the reducing agent. And you define the agents in the atoms oxidized and reduced from the reactants. You're looking at the reactants for their change into the products. So the reducing agent is copper. Copper is the reducing agent, and HNO3 is the oxidizing agent. So we're looking at D. A balloon is filled with air at room temp. It's immersed in liquid nitrogen, at which has a temperature of 77 Kelvin. Well below room temperature, the balloon contracts and shrivels up. The air inside the balloon, what are its signs of Q and W? So the Q in the balloon, the heat of the air inside the balloon has been released, has lost its heat. Okay? So heat in the balloon has dropped because the temperature's dropped. Temperature of the air in the balloon dropped, heat dropped. And then the work was absorbed by the balloon because the surroundings were working on the balloon, compressing it, changing its volume inward. So the volume decreased. So that means that the surroundings were working on the balloon, so the work is actually positive. So the sign of W in the balloon would be positive. So we're looking at D. So the balloon releases heat to the liquid nitrogen, or the heat was absorbed by the balloon into the liquid nitrogen, and then the liquid nitrogen was working on the balloon to compress it inward. Identify the reaction that represents the standard enthalpy of formation of the noted compound. So we want 1 mole of the compound as a product. Well, they all have 1 mole, but then we want elements in their standard states and everything to balance out accordingly. So that looks good. 5/2 H2 looks good. Carbon solid O2. So D looks like the right answer. C is not the right answer because the standard state of nitrogen is not N. The standard state of hydrogen is not H. Carbon's not gaseous. You're looking for the standard state of the element at room temperature. So N2 gas, H2 gas, carbon solid, O2. Now there's a lot of elements where we may not know without looking these up. Certainly not ozone. That's a more less stable allotrope of oxygen. So it's not A. B makes no sense. So we need elements on the reactant side, but in their standard stable states. So the ones I would know, H2 gas, and the things that all share gas. So that would be F2, N2, O2, Cl2, all the noble gases. So all the noble gases are gases at room temperature. Bromine is Br2 liquid. Iodine's a solid. Carbon's a solid in the form of graphite. Some other solids would be P4, S8 in terms of solids. Metal solids for the metals, with the exception of mercury, which is a liquid. Mercury and bromine, the only 2 liquids on the periodic table. So an acid solution is 0.1 molar in HCl, 0.2 molar in H2SO4. What volume of 0.5 molar KOH must be added to 500 milliliters of the acidic solution to completely neutralize the acid? Okay, let's try to solve this with dimensional analysis. So what volume of the KOH solution in milliliters is what we're looking for? Let's start with the acid. So the acid solution is 0.1 molar HCl. The reaction taking place is HCl reacting with we have two different acids present. That's what's kind of tricky on this problem. So we have acid and H2SO4 that are going to be both reacting with KOH to form K2SO4 plus KCl plus H2O. Next, we're going to get three of them if we balance this all out. So we're going to need three KOHs. Okay, another way of another way, I'm trying to think of how we might, all the different ways we might solve this reaction. I might look at these two reactions separate, actually. Maybe an easier way to think of this problem. To think, okay, I'm going to take H2SO4 plus 2 KOH, go to K2SO4 plus 2 waters, and then in reaction 2, think about HCl plus KOH going to KCl plus H2O. Okay, because I can think of how much KOH it's going to take to neutralize the H2SO4 perhaps first, and think how much volume it's going to take to neutralize the HCl, and then just simply add them together. Okay, so we have 500 mils of the acidic solution, so I have 0.500 liters of the acid solution, 0.200 molar H2SO4 per liter, and then I will need, for every 1 mole of H2SO4, I'll need to add 2 moles of KOH, and then for every 0.150 moles of KOH, that's 1 liter of that solution. And then a liter is 1,000 milliliters. And so if I carry out the first step here, so 0.5 times 0.2 times 2 divide by 0.15 times 1,000 milliliters. I can write that out here. 1 liter is, I can move this over. Let me actually rewrite this here just for that last step. So the last step was just converting to milliliters. So 1 liter, 1,000 milliliters. So that's 1333 milliliters to neutralize just the H2SO4. So 1333 milliliters of KOH. Then I go through the same set of steps for HCl. Now HCl is half the concentration and only has 1 H+. So it should only be a quarter of that. If I divide that by 4, add that back to 1333. So it's looking like it's going to be A. Now the reason why I can easily do that math is, HCl is half the concentration of H2SO4 and only has 1 H+. H2SO4 had 2 H+. So it's only going to take a quarter of the KOH. We can write this out and see this accordingly because it would just be, let me move some of, I can't erase in a video. But what I want to do is just change this here to 0.100 mole of HCl per liter, and then change this to just then be 1 mole of KOH per 1 mole of HCl that are needed, and then from there the math is the same. So if I go 0.5 times 0.1 times 1 divide by 1 divide by 0.15 times 1,000 milliliters in a liter gives me 333. So 333 milliliters to neutralize all the HCl solution. So adding these up, 1333 plus 333 gives the 1670. If we're tracking these, that's 3 sig figs, that's 3, so that's why we're rounding just the 3 sig figs in our answer. Okay, yay. All right, so let's move on to the next question. In the thermite reaction, where does the energy come from? Our choices are breaking bonds in the reactants, breaking bonds in both of the reactants, forming bonds in the products, or in one of the products, forming bonds in both of the products. If you ask me this question, I've always hated this question because the energy comes from the difference of the energy it takes to break the bonds in the reactants versus those you get back in the products. And we haven't quite talked about metallic bonding, but there are bonds in metal solids, of course. There's things holding aluminum together, that's why it's a solid. And there's ionic bonds holding the iron oxide together. And there's bonds here and there's bonds here. So the real answer the energy comes from, the reason why thermite releases energy is because the energy it takes to break the bonds and the reactants is lower than the energy you get back when you make the new bonds in your products. But the person who wrote this question thinks they're being clever, in that it's the energy comes from making the new bonds. So energy making bonds is exothermic, breaking bonds is endothermic. Despite the fact that this is just a formalism or an approximation technique, and it's really not how the reaction necessarily occurs in the first place. So it's really a stupid question. The real reason the reaction releases energy is because of the difference of the bond strengths of the products compared to the reactants. And oh, by the way, there are bonds in the metals, which we haven't exactly talked about that much, but there must be something holding the iron together. So it's the bonds in both of the products. So I think the answer should be something about the difference between the reactants and the products. But the true answer that the author of this question was looking for was just the form bonds in the products. So select the image representing the enthalpy change for an endothermic chemical reaction that involves breaking and forming bonds. And so an endothermic reaction is one where your reactants and your products differ in enthalpy such that the products are higher. So this one is the correct answer. So we're breaking the bonds. That's the energy to break the bonds. This energy we get back when we make the new bonds. So this is not showing, this would just be a reaction where you only break like one bond. So this might be the H bond making two H's. This might be like two O's coming together to make O2. We're just taking already a broken bond and making a new bond. This is going to be breaking bonds, making new bonds where it's exothermic. So this one's exo, this one's endothermic. So at the top of the image are contour representations for the 2s and the 2p orbitals, or 2s and the 2p. Use a relative size of these orbitals to answer the question. So which statement correctly identifies the orbital and its number of nodes? Okay, so the idea here is that this size is similar, so, and it's just rotated to the y-axis. It's really hard to see, but this is just a pz orbital. The 2pz orbital, it's on the z-axis. This is the 2py orbital. Okay, and so then 1 and 2, so this must be like a 3s or a 4s orbital. And then this must be like perhaps like a 3px orbital or something like that. Okay, so which statement correctly identifies the orbital and its number of nodes? Okay, so 1 is a 3s orbital, 0 nodes. Well, the 3s orbital has 2 radial nodes. So A is not correct. So the first part could be correct, but the second part would not be correct. 2 is a 3px orbital with 1 node. Could be the 3px orbital. The 1 node, this is something we haven't quite talked about this semester, but it would actually have 2 nodes. So it's going to have 1 radial node and it has the 1 angular momentum node. But don't worry about the radial node for p orbitals. It's not in the book. I don't know why a question like this is appearing. So, but that one is incorrect because it would actually have 2 nodes as well. So 1 angular plus 1 radial. And then where that radial comes from is not something we've talked about. 3 is the 2p y orbital with 1 node. That is the correct answer. We kind of know that it should have 1 node, though, that the 2p orbital should at least have that 1 angular node from the angular momentum quantum number being equal to 1. So I think that makes sense for us. And so 3 is correct. 2 is a 2px orbital is wrong because it's too small. Like the size of the orbital increases, so the n value should increase. So if you ask me, kind of a silly question on exactly what it's asking and why it's getting into some of these more complicated radial nodes for functions that aren't in the book, make it a little bit complicated. But I wanted to point out this question in case you come across it and are confused by it. What is the oxidation number of carbon in this compound here? So we haven't gone through too many compounds, or complicated ones at least today. The way I like to break this apart is we know ammonium has a plus charge. There's 2 of them, so the entire C2O4 is a 2 minus. Okay, so C2O4 their oxidation numbers have to sum up to be equal to 2 minus. So we can take a -2 oxygen, that's -8 overall. We know that that has to be the oxidation number of C2O4. The oxygen there is just the ordinary -2 oxidation number. Only exceptions are peroxides, superoxides, which only form in rare cases, and compounds with fluorine. So we'll know we have a super or peroxide because we'll have something like NaO2, that's sodium superoxide, or K2O2, that's potassium peroxide. K2O is just potassium oxide. So the oxidation number of O is -2, -1, -0.5 accordingly, because we know the charges of the metal here very easily. Okay, so the peroxides and superoxides work themselves out. Compound with fluorine might be something like OF2. The fluorine's always -1, two of them -2, make oxygen a +2. So just trying to show that oxygen is not one of its exceptions, is just the ordinary -2, four of them -8, have to get -2 overall, so the two carbons together have to be +6 to get -2. +3 overall. So the oxidation number of carbon, and this is actually the oxalate ion, would be +3. So +3 times 2 is +6, -8 overall, -2. Okay, if it takes 1.57 times 10 to the 18 joules to break the bond in an N2 molecule, which of these will break the bond? Okay, so we're given multiple different types of radiation. Okay, so we get the energy per one single molecule. E is equal to h nu. So in terms of a frequency, we could solve for the frequency of light associated with this transition by taking E and dividing it by Planck's constant. And so that'll give us the frequency of light that we need. And so let's do that math real quick. So we take 1.57 times 10 to the -18, divide by 6.626 times 10 to the -34. That gives us a frequency of 2.37 times 10 to the 15 inverse seconds. So the frequency needs to be greater than or equal to this. We want the frequency to at least be this to match that energy, or be greater in frequency. So microwave radiation has a frequency that's relatively low. That's not enough energy. So not enough energy by microwave radiation. Ultraviolet radiation sounds pretty good, and probably X-ray does too. So one would at least make sense. You know, the X-ray is going to be the highest energy of all of these, so an X-ray better break it. Or possibly it won't. So maybe we need to work out the energy as well. Okay, so the other thing we might do is we could say, well, like two things we could do. What's the energy of this photon? Is it greater than that energy or less than that energy? That's probably the easier calculation to do. So let's do and use E is equal to hc over lambda, calculate the energy of that photon. So that would be 6.626 times 10 to the -34 times 2.998 times 10 to the 8 meters per second, and divide by 300 nanometers. That's 300 times 10 to the -9 meters. That gives 6.6 times 10 to the -19. And that is less than 1.57 times 10 to the -18. So that's less than the energy the N2 bond needs to absorb to break. So 2 is not going to work. Now, the X-ray radiation with the wavelength of 1 nanometer, that's really short wavelength. That's should be a really high amount of energy. Let's calculate that. So the energy here, just dividing by 1 nanometer, so 6.626 times 10 to the -34 times 2.998 times 10 to the 8 meters per second. And then divide by 1 nanometer, 1 times 10 to the -9 meters. That's 10 to the -16. So that corresponds to the X-ray radiation corresponds to 1.98 times 10 to the -16 joules, which is of course greater than the energy it takes to break the bond. So 1 works, 2 and 3 don't. So that's the best answer. Which experiment supports the de Broglie theory that matter has a characteristics of a wave? And so it's the diffraction of electrons. So when you pass electrons through matter and then they're deflected, kind of shows that those electrons have a wave, and if they hit matter and are deflected, off the matter, then you get a particular pattern indicative of the crystal structure of that matter. So the diffraction of electrons by matter, that's X-ray diffraction, sort of supports the de Broglie theory of electrons. So these other things don't do much of it. The photoelectric effect is just one photon is absorbed by one metal to release an electron, or by one bond to break it, or given off by one atom like a hydrogen atom as it changes energy levels. Diffraction of visible light really doesn't have much to do with the theory of particles having a wave behavior, so you need to have the diffraction of an actual particle. And so particles are deflected, showing that they have a wavelength associated with their path of trajectory, and refraction of light through a prism that's useful in an experiment but has nothing to do with this particular question. Okay, so here's some additional questions. So the boiling of water is an example of what type of reaction? So water boiling is water liquid going to water gas. Where I come from, you have to add heat into water to make it boil. So that means that water boiling is endothermic. So that's an endothermic reaction, and then because the has a positive delta H, so endothermic and positive. Which statement is true when 4.75 grams of magnesium reacts with excess oxygen? So heat is being released because it's exothermic, so heat is being released. And so then we have, this is the heat released for every 2 moles of magnesium, and then 4.75 grams of magnesium, we have to convert that into moles, so multiply by the number of moles of magnesium that are actually reacted here. So convert these grams to moles, work this out, but the key is you got to put the 2 moles of magnesium per heat change of the reaction. So heat's being released by this reaction. Which statement is true when ammonium nitrate is dissolved in water? So the reaction is endothermic, so the reaction is absorbing heat because it took it from the surroundings. So the temperature rises, so this is occurring in a solution, the solid's being added to water. And so the solution temperature should be dropping or decreasing, so the solution temperature drops in temperature because the reaction released some of its heat. Nope. The solution temperature drops because the reaction absorbed some of the heat. So the reaction absorbed some heat from the solution as it was taking place, so the temperature drops. What is the designation for the subshell? N equals 4, L equals 2. So N4 would be the 4, and then S is 0, L is 1 is P, L2 is D. So that's the 4D subshell. What is the maximum number of electrons that can occupy the 5F subshell? The electrons occupying orbitals come from the M sub L and M sub S quantum numbers. So the 5F subshell is the N equals 5, L equals 3. M sub L could be minus 3, minus 2, minus 1, 0, 1, 2, and 3. So that's 1, 2, 3, 4, 5, 6, 7 orbitals. 7 times 2 is 14 electrons. So 14 electrons can occupy an F subshell. What is the range of possible values for the magnetic quantum number that's told to us? That's the M sub L quantum number for the below orbital. Key here, this is one of the D orbitals. This is the D, let's see, it's in the Z plane and the Y. So it's the D, Y, Z orbital. One of the M sub L's could range from minus 2 all the way to plus 2 and all the integers between. So the range of possible values for M sub L could be minus 2, minus 1, 0, 1, or 2. Okay, so this orbital would have one of those. Now, one of the D's doesn't match up to one of those numbers. It just means one of the D's has one of the numbers. The other 4 D orbitals have then the other 4 set of quantum numbers. How many unpaired electrons does a ground state sulfur atom contain? So the unpaired electron sulfur is a neon, 3s2, 3p4, like oxygen. So 3s and then the 3p subshell would look something like the 2s electrons spin paired, and then 1, 2, 3, 4. So we should have 2 unpaired electrons. How many electrons in a ground state chlorine atom have a angular momentum quantum number of 0? So let's look at the full configuration of chlorine. 17 electrons, 17th element on the periodic table. So 1s2, 2s2, 2p6, 3s2, 3p5. How many have an L value of 0? Well, the L is equal to 0 here, L is equal to 0 here, and here. This is L equal 1, L equal 1. So there's only 2, 4, 6 electrons that have an L value of 0. This is a word question. Seems strange. This is just a thought problem of trying to solve a question about quantum numbers relating to a particular configuration. So this is specifically for this atom. How many of its electrons can have an L value of 0? Which atom below contains a total of 4 valence electrons? Well, carbon has 4. It's 4 over from the left side of the periodic table, so carbon makes sense. Everything in carbon's group also has 4. Okay, so your filled F and D subshells don't count towards the valence. So let's just do lead to show that. So lead's configuration would be a krypton. Let me actually, I don't have the periodic table handy. Let me quickly look at this to make sure. So lead would be actually a xenon, followed by a 6s2, 4f14, a 5d10, and a 6p2. That's our outermost shell. That's our 4 valence electrons. The filled F and D block don't count towards valence. So these aren't being counted towards our outermost electrons once they're completely filled. If they're empty, they count, or if they're not totally filled, they wouldn't be counted. So like if we're counting the valence counted like vanadium. So vanadium's configuration would be argon, 4s2, 3d3, 5 valence electrons. You get the zinc or past zinc in the 4th row. The 10 wouldn't be counting in the 3d. So only 4 valence electrons for lead, just like carbon. So if you know carbon has 4 and lead's in the same column as carbon, you know they all have 4. So all the above have 4 valence electrons. Final page here, final 2 questions. So an atom has an anomalous configuration of argon, or of krypton, 5s1, 4d5. What's the element? Well, that's easy. We just count the electrons. So 36 for krypton, plus 6, so that's 42. Element 42 is MO, it's molybdenum. So molybdenum, now how many unpaired electrons? Well, we have the 5s and the 4d. 5s1, 4d5. So we have a total of 6 unpaired electrons. In the expected configuration, we would have only had 4. We would have expected it to be 2 here in the 5s, and then the 4d, we've only expected to have 4 electrons. But we removed one of these and flipped its spin around, applied Hund's rule, so we get 6 unpaired electrons. Okay, so then what is the electron configuration of neodymium, which does not have one of these weird anomalous configurations? So let's look at our periodic table. It's element number 60. So 60 electrons have to go in. Nearest noble gas is xenon. Xenon 6s2, 4f, and then it's 4 across. And our double check here would be 54 electrons here, plus 2 for 56, plus 4 gives us 60. So you can count the electrons assigned and make sure that they match. So xenon 6s2, 4f4. All right, well, that's all of our review problems that I've selected to go over. Hopefully this gives you some good help for preparing for the midterm. If anything today doesn't make sense, make it make sense. That's the best advice I could give all of you guys looking into studying over the weekend here, is make things make sense. And until they do, keep reading, keep working problems, keep asking questions. Shoot me an email. I got office hours Monday, 2:30 to 4. And TA room's open Monday. And like I said, just use your book, use the videos that are provided, just somehow seek out the answers to the questions you have, and hopefully you'll be able to find those and move forward. All right, good luck on the test. Thanks for listening.